a problem, and we have fixated to our 2D problem. So what we have completed, this is from last week, okay? We are able to deal with the element. So we have done from element. Okay, we have dealt with element. Okay, and then from element, we go to Mohr circle. Okay, and I'd like you to draw this, please, if you could. Okay, so at point X over here, this is how your element is orientated at point X, and this is your X. Okay. And then on Y, you draw an element that is exactly what I'm drawing now based on that orientation. And now this is your Y. Okay. So the next thing that we're going to find out is we are going to find out our 2 theta P. And I want you to watch the arrow. Okay. So 2 theta P, right, is from point X to stress 1. I repeat again, from point X to stress 1. If you do from point Y, it's also what? 2 theta P. And based on its rotation, it's going to rotate anti-clockwise. Okay? It's going to be rotating anti-clockwise. So the next thing that we're going to, this is the continuation. We are going to find out what is tangent 2 theta P. And this will be equal to 500 divided by 275. Okay? So from here, your 2 theta P will be equal to 500 divided by 275 inverse tangent. So it's 61.2 degrees. Okay, and you have to write the directions anti-clockwise. And then theta P is equal to 61.2 divided by 2 is equal to 30.6 degrees anti-clockwise. Okay. So if I were to take a protractor, measure, yeah, it's about 60 degrees, okay, or 61.2 degrees. So what it means is this, okay? So now, to be at this point, okay, we have to rotate our element in the anti-clockwise direction. Okay. And this anti-clockwise direction, so this is our point what? This is our point X. Okay. So if we draw a vertical line, this angle that we have rotated is what? It is, for the element, it is 30.6 degrees. Okay. Now, if you were to do from point Y, if you were to do from point Y, the orientation is the same also. Only thing now, your point Y, this is your original Y, so you rotate in this angle, right? You rotate at this angle by 30.6 degrees. Okay, and then this is now currently your Y. Okay, your Y surface. Okay, so the Y surface and the X surface has been rotated anti-clockwise by 30.6 degrees. Okay, now the next thing we have to deal with is what are the associated stresses. Okay, what are the stresses? Okay, so I'm going to take this whole thing. Bear with me. I'm going to copy, and it usually don't work. And then I'm going to paste. Oh shit, it works. Okay. Okay. So now we have to deal with the element, because when we draw the element, it has to have the stresses on the element. Okay, so watch this. Okay, so the first thing that we draw is we sketch our 0, 0 axis. Okay, so over here now, this is our original element. And our original element, we label this as X, and we label this as Y. Okay. So now the principal plane is such that we have to rotate how many degrees? 30.6 degrees anti-clockwise. Okay. So 30.6 anti-clockwise. I don't know whether can I do this. I'll try. Hold on. I'm going to use a different color now. Okay. And then I'm going to rotate this by 30.6 degrees, or, 30 degrees. I cannot get a 0.6. Okay. Okay. So the red is the axis that's rotated by what? 30.6. So if I'm going to rotate this by 90 degrees, we're good to go. Boom, boom. Okay. So the red that I've drawn is basically a rotation, okay, anti-clockwise by 30.6 degrees. Okay. Why 30.6? We calculate over here, theta P is 30.6 degrees. Okay. From here, I'm now going to construct an element in red. Okay, repeat again. We are going to construct an element in red. Not perfect, but good enough. Okay. So that element is rotated 30.6 degrees anti-clockwise. Okay. And a good practice is to do this now. Okay. So draw a line at this corner over here and label this as your point X initially. Okay. And then draw another line horizontally at the edge over there. And this is originally your point Y. Okay. Okay. The next thing I want you to do, don't write anything. Watch the screen. Okay. Don't write anything. Okay. If we were to look at Mohr circle, from point X, if I rotate by 61.2 degrees, I get a stress state of 1, which is equal to 645.635 megapascal. Okay. That is on Mohr circle. On the element, you can see this point X now, yes or no? We are going to rotate by how many degrees? 30.6 degrees, and this value will correspond to a tensile load of 645 degrees, 645.635 megapascal. Are we clear? Right? You can see a direct what? Relationship. Okay. Okay. I'm going to do this again. Okay. From point Y now. Okay. We are going to rotate again in an anti-clockwise direction, and we are going to reach a stress state of minus 495. Okay, so stress 2 is equal to minus 495.635 megapascal. Okay. So again, from point Y, we have to rotate in an anti-clockwise by 30.6, and this results in a compression stress of 645 0.635. No, minus 495 under compression, 495.635 megapascal. Are we clear? Okay, so what we have just done is we have done a sequence where we go from Mohr circle to what? To element. Okay, we have done an example that so this is known as our principal plane orientation. Are we clear? Okay. Now, in the second part of the question, if we were to look at the question, they ask another sort of information. Okay. They also want to know the maximum in-plane shear stress. Okay. The principal stress and the maximum in-plane shear stress. Then we have to relate to the element again. Okay. Now, maximum shear stress occur where? Over here is where we have our what? Tau max. And over here, okay, over here, again, is where we have our tau max. Okay. So the tau max okay, element for tau max now, we now have to find the other angle. And this angle over here, right, will be equal to what? So the angle over there will be equal to 90 minus by what? 61.2. So 90 minus 61.2 is equal to, I'll do down here. So the angle, okay, will be equal to 90 minus by 61.2. And now this is equal to 28.8 degrees. And this is such that it's going to rotate in the what? Clockwise direction. So in the element, we have to rotate 28.8 degrees divided by 2. 28.8 divided by 2 is equal to 14.4 degrees. And we have to rotate in a clockwise direction. Okay. So now, how is this going to work? Okay. Now, we are going to sketch the element again. Okay. We have our element, our original. Okay. So this is our original element. Okay. So this is our point X. Everything the same again. This is our point Y. Now our rotation is different. Okay, we have to rotate 15 or 14.4. We rotate by 14.4. Okay, so in a clockwise orientation now. So I'm going to now rotate this by 14.4. Okay, I'm going to use red. We're going to rotate this by 14.4 degrees, approximately. Okay. Then I'm going to flip this by 90 degrees. Okay. So now I'm going to sketch our element now. Okay, now I'm going to sketch our element. So I'm going to sketch our element like what I did before. I'm going to sketch in red. Okay. Okay. So in this case, you draw a vertical line. You know that this is your X. and you draw a horizontal line, you know that that is your what? That is your original y. Okay. So this rotation is rotating at 14.4 degrees, and we are rotating in a clockwise. Okay. Okay. So if you look at the Mohr circle now, we know, we are aware that at this point, our coordinates is 75, and then we have the shear to be what? The shear over here is minus 570.635. Okay. And then at the top, we know that our normal stress is 75, and then we have positive 570.635. Now, the positive and negative in shear don't mean anything at all. Yes or no? Right? It all depends on the rotation of the what? Element. Now, so we know what is common is this, okay? The normal stress for both surface A and surface B are going at what? Are going at 75. Both C tensile of what? 75. Yes or no? Because the normal stress is 75. Okay. Now, the next thing I want you to do, watch me. Don't write anything. Okay, you write something, you'll get lost. Okay, watch me. Now, I'm interested in this surface over here. Okay. And this surface, to get to that surface, I need to rotate